We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
The main thing Chandra does is take these superb, sharp images.
Ordinary matter, or the stuff we and everything around us is made of, consists largely of empty space. This is because matter is made of atoms, and an atom is a cloud of electrons orbiting around a nucleus composed of protons and neutrons. Suppose we could generate a force strong enough to crush all the emptiness out of a stone roughly the size of a football stadium. The stone would be squeezed down to the size of a grain of sand and would still weigh 4 million tons. Now imagine something that dense that is not the size of a grain of sand, but rather the size of the island of Manhattan. That's a neutron star, one of the most exotic objects in the universe. Slavko Bogdanov of Harvard University explains how neutron stars are born.
Neutron stars are created when a massive star runs out of fuel and collapses. As the star collapses, the density becomes so immense that protons and electrons are squeezed together tightly to form neutrons. The end result is a star only 20 kilometers across, but weighing 1.5 times more than our Sun, and made up mostly of neutrons. These exotic objects possess enormous gravitational fields, about 100 billion times stronger than what we experience on Earth, and have very strong magnetic fields.
Once a neutron star is formed, however, it does not mean that it just sits quietly in the cosmos. Rather, neutron stars have been found to do some incredibly interesting things that astronomers are still trying to understand.
Neutron stars are the most rapidly rotating stars we know about, with the fastest spinning at an incredible rate of over 700 times per second. For many neutron stars, the strong magnetic field and fast rotation create a giant electric generator, which forms a deadly beam of high-energy particles. As the neutron star rotates, the radiation from the particles appears to pulse, analogous to a rotating lighthouse beam. Such a neutron star is called a pulsar. The wind of fast-moving particles generated by a pulsar can also produce a large glowing cloud surrounding the star, called the pulsar wind nebula. Most of the radiation from pulsars is observed at X-ray energies, so Chandra is a valuable tool in the study of these intriguing objects.
So while some neutron stars are these stellar whirling dervishes, others are intriguing in other ways. For example, there's a class of neutron stars called magnetars that have magnetic fields that are about 1,000,000,000 times the Earth's. That's a 1 followed by 15 zeros for those keeping track. Dr. Bogdanov explains what these intense magnetic fields can do to a star.
The immense magnetic field of a magnetar exerts enormous strain on the crust of the neutron star. On rare occasions, the strong magnetic forces can break apart the crust, resulting in a powerful starquake, similar to how upheaval within the Earth causes earthquakes. Such starquakes are among the most violent events in the universe and release tremendous amount of energy, much of it in the form of X-ray radiation. By catching one of these outbursts in the act and following its behavior over time with X-ray telescopes such as Chandra, we can learn a great deal about the extreme conditions at the surface of these exotic stars.
Clearly, neutron stars are unlike anything we know about here on Earth, and because they are so extreme, they give scientists a chance to test their ideas about matter in a way that just can't happen in a laboratory. No matter what flavor of the neutron star, each one is a chance to learn about the fundamental laws of physics that rule our universe. For more information, visit our website at chandra.harvard.edu.
This was a production of the Chandra X-ray Center, Cambridge, Massachusetts. NASA's Marshall Space Flight Center manages the Chandra program. The Smithsonian Astrophysical Observatory controls science and flight operations from the Chandra X-ray Center.